For most of our lives, we've believed the same old story about Mars, that it's a cold, dry, and failed world. But what if Mars didn't actually die? What if it simply went quiet? In recent years, radar has pierced through the dust to reveal traces of ancient flowing water. We've discovered strange minerals proving that this planet remained wet for millions of years. And then, there's one detail that has left the scientific community breathless. Tiny leopard spots found on a single, lonely rock. Now, to be clear, this isn't a headline about aliens. This is a piece of scientific evidence, handled with caution, yet filled with promise. Why are scientists more excited today than they've been in decades? And if Mars once struggled to hold on to life, what does that tell us about our own place in the universe? To understand why this matters, we first need to see Mars the way it actually is today. That red color is why it's called the red planet. It isn't fire, it isn't heat, it's rust. Fine iron oxide dust, ground down over immense time and spread like powder across the surface. If you could stand there, the world would feel quietly wrong in small ways. The sky wouldn't be blue. Instead, the sky would take on a muted yellow-brown tone, often described as butterscotch, caused by fine dust suspended in Mars's thin atmosphere. And at sunset, the familiar rules flip. Instead of a red horizon, Mars can glow blue near the setting sun, an eerie inversion caused by the same dust scattering light differently than it does on Earth. But the strangest part is the feeling. Mars has air, but barely. Less than 1% of Earth's surface pressure. Not enough to hold warmth. Not enough to soften radiation. Not enough to carry sound in the way we expect. Light seems harsher, shadows sharper, and the silence feels almost physical. It's easy to look at Mars like this and assume it never had a chance. And once we look past the surface, Mars begins to tell a very different story. When a spacecraft lands on Mars, it doesn't do so by chance. Every landing site is the endpoint of years of debate, disagreement, and careful compromise. Because on Mars, where you land determines the question you're trying to answer. Each site represents a hypothesis. In 1976, during the earliest era of planetary exploration, NASA sent Viking 1 and Viking 2 to the Martian surface. They weren't looking for ancient landscapes or subtle chemical clues. They were looking for life directly. Viking carried the first biological experiments ever sent to another planet. The results were confusing. Some tests reacted as if microbes might be present. Others showed nothing at all. At the time, the data sparked excitement, and then skepticism. In the end, scientists concluded the signals could be explained by unfamiliar chemistry in the Martian soil. Viking didn't give us a clear answer, but it gave science something just as important: caution. Mars had taught us our first lesson, that extraordinary claims demand extraordinary care. Decades later, missions became more focused. Instead of asking, "Is there life right now?" scientists began asking a quieter question: was this place ever capable of supporting life at all? That shift in thinking led explorers to Utopia Planitia, a vast plain in Mars's northern hemisphere. From orbit, the region hinted at something unusual. The terrain was smooth, low, and ancient. Exactly what you might expect from a long-vanished ocean basin. In 2021, China became the second nation to operate a rover on Mars. It carried radar designed to look beneath the surface, not for fossils, not for organisms, but for structure. What it found were layered formations underground, patterns consistent with sediment laid down by water. They didn't prove an ocean once existed there, but they made the idea harder to ignore. Mars, it seemed, had regions shaped not by a single flood, but by water that lingered. Far to the south, another site drew even more attention. Jezero crater doesn't look dramatic at first glance. A shallow bowl, gentle slopes, quiet terrain. But from above, something stands out. A fan-shaped structure at the crater's edge, a delta. On Earth, deltas form when rivers slow down and deposit sediment into standing water. They are excellent at preserving history. Layer upon layer of material laid down gently over time. That made Jezero special. If Mars ever had a lake that lasted long enough for chemistry to settle, for minerals to form, and for environments to stabilize, this was one of the best places to look. That same year, 2021, NASA landed another rover. By the time Perseverance landed, Mars exploration had changed. The goal was no longer to rush to conclusions. It was to collect context. Each landing site, Vikings Plains, Utopia's buried layers, Jezero's ancient delta, added a chapter. Not a verdict, a history. Mars wasn't being interrogated anymore. It was being studied. And through that process, one truth became clear. We didn't fail on Mars. We learned. Mars was no longer just a distant surface of rock and dust. It was a world with a past, shaped by forces that took time, patience, and water to leave their mark. And what those carefully chosen places began to reveal was something no one could ignore. Mars had been shaped again and again by water. If you want the clearest evidence that Mars once had water, you don't start at the surface. The surface is where Mars keeps changing. Dust storms, wind, radiation, and extreme temperature swings slowly blur whatever came before. It's dramatic, but unreliable. Like a page that's been erased and rewritten too many times. The real record lies below. That's why some of the strongest discoveries about Mars haven't come from images, but from instruments that can see into the ground. Ground-penetrating radar works by sending pulses downward and reading the echoes that return. When those echoes change, they reveal differences in material, layers, boundaries, and buried structures. And on Mars, those structures tell a quiet but powerful story. Radar scans beneath parts of the northern plains have revealed stacked layers underground, extended bands that stretch across wide areas. These are not chaotic deposits left behind by a single violent event. They are organized, repeated, built up over time. Even more telling is their shape. Some of these layers lie flat, while others slope gently, forming tilted patterns that resemble ancient shorelines on Earth. That detail matters. A shoreline isn't created by a brief splash of water. It forms when water holds its position long enough for sediment to accumulate again and again. In other words, it suggests stability. Chemistry supports that picture. Across Mars, orbiters and rovers have identified hydrated minerals. Minerals that form most easily when water interacts with rock over extended periods. These aren't traces of a momentary wet surface. They are chemical signatures of contact, repetition, and time. On a planet where liquid water is unstable today, finding those minerals is a clear signal that conditions were once very different. And the pattern doesn't stop there. When scientists compare the distribution of valleys, channels, and sediment deposits, a broad direction emerges. Much of the ancient flow appears to have moved from the higher southern regions toward the lower northern basins. Mars, like Earth, has gravity. Water follows it. The northern lowlands sit thousands of meters below the southern highlands. If Mars ever had long-lived bodies of standing water, this is where they would naturally collect. That's why the idea of a northern ocean has persisted, not because it's dramatic, but because it fits the physics. Repeated flow, downhill movement, and sediment settling over time leave recognizable signatures. Radar adds weight to that argument by revealing what wind alone cannot explain. What makes these underground records so important is what they imply about duration. These are not signs of a brief wet phase that quickly vanished. The layering suggests processes that repeated and accumulated, conditions that returned or persisted long enough for geology to keep track. That kind of timescale matters. Tens of millions of years is not a blink in planetary history. It's long enough for lakes to stabilize, for deltas to build, and for chemistry to move beyond randomness. It's long enough for environments to become predictable. And predictability is what makes habitability possible. Mars didn't just experience water. It experienced water that behaved consistently enough to leave an archive beneath its surface. An archive that survived even after the planet changed. It's as if Mars kept a record of its own past, knowing the surface would eventually forget. Once you accept that, the story shifts. Mars is no longer a planet defined by a single wet moment early in its history. It becomes a world shaped by water that lingered, returned, and left structured evidence behind. That realization brings us closer to a simple conclusion. Mars once had conditions that look uncomfortably familiar. But just as the picture begins to feel clear, one detail refuses to fit neatly into the timeline. But something about this water didn't behave the way we expected. For a long time, the story of Martian water sounded clean and simple. Mars was wet very early, then it cooled, then it dried out. And everything we care about, rivers, lakes, habitability, was sealed away in the deep past. That timeline is comforting because it's tidy. But Mars has never been tidy, and one of the most unsettling clues comes from a place that looks almost boring at first. Sand dunes. On Mars, dunes are everywhere. Dark, wind-shaped waves of sand that migrate slowly across the landscape. We expect dunes to be dry. We expect them to be loose. We expect them to behave like sand does on Earth. But in some regions, scientists have found something that doesn't fit that expectation. A hardened crust, almost like a cemented skin, sitting on top of dune surfaces. It isn't just a thin dusting, it's a firm layer. It can crack, it can break into plates, and it can be noticeably thicker than a simple coating of wind-blown dust. That detail matters, because wind is a sculptor, not a glue. Wind can pile sand into ridges. It can carve patterns. It can sort grains by size. But wind cannot easily turn loose sand into a hardened crust that behaves like it has been bound together. To create something like that, you usually need chemistry. And chemistry, most of the time, needs a small amount of liquid, not oceans, not rainfall, just enough moisture to dissolve salts, move through the pores between grains, and then evaporate, leaving minerals behind like mortar. That leads to the most plausible explanation: brine. On Mars, pure water is unstable at the surface for long. The air pressure is low, temperatures swing hard, and water tends to freeze or evaporate quickly. But salty water behaves differently. Salts lower the freezing point, and in certain conditions, a thin film of briny liquid can briefly exist, long enough to wet grains, dissolve minerals, and then disappear. If that happens repeatedly, even in short episodes. It can slowly cement sand into a crust. Picture it like this. A tiny amount of salt water seeps into the dune surface. It doesn't flow like a stream. It doesn't make puddles you could see from orbit. It simply dampens grains. Then it evaporates. The dissolved salts are left behind, crystallizing between sand particles. Over time, those crystals bind the surface together, grain by grain, until the dune develops a hardened skin. That process is subtle, but the implications are not, because it suggests that Mars didn't just have water long ago. It suggests Mars may have had wet episodes much later than the ancient river valleys and lake basins most people think about. In other words, the planet's wet story may not be a single chapter that ended billions of years ago. It may be a pattern, quiet, intermittent returns, and the clues don't appear in isolation. These crusts are found in specific contexts, where the terrain, the sediment, and the local conditions make moisture, however brief, more plausible. They sit in places where Mars's surface materials and salts can support briny chemistry, where wind alone doesn't explain what's being seen. That's what makes this evidence feel so disruptive. It doesn't demand a warm, blue sky Mars. It doesn't require a thick atmosphere returning overnight. It doesn't claim oceans were still rolling on modern Mars. It only asks you to accept something much more uncomfortable. That even on the cold Mars we know today, there may have been moments, later, newer, and more recent in geological terms, when liquid played a role on the surface. And once you accept that, the timeline changes. If brines could appear and disappear in cycles, then Mars may have remained chemically active for longer than we assumed. It may have offered brief windows where water interacted with soil and rock, long enough to leave behind minerals, textures, and crusts that wind can't produce by itself. That doesn't mean life existed there, but it does expand the period when habitability was at least possible. It stretches the margin of time where environments could form, fade, and form again, like a door that kept opening just a crack long after we thought it had slammed shut. Mars didn't just lose its water, it kept finding ways to bring it back. And now the question becomes less about whether Mars was wet once, and more about how a planet can keep revisiting water, even as it grows colder and thinner and quieter. Because if Mars had late, repeating wet episodes, if the planet could briefly wake up and then fall silent again, then we need a different kind of clock to understand it. And to understand how that was possible, we need to look at Mars on a much longer timescale. To understand how Mars could experience these later wet episodes, we need to step back, far back, and look at the planet's climate on a much longer clock. Mars does not change the way Earth does. On Earth, we think in seasons. Winter, spring, summer, fall. Predictable rhythms that repeat every year. Mars operates on a very different scale. One of the key differences is the tilt of its axis. Like Earth, Mars is tilted as it orbits the Sun. But unlike Earth, that tilt is not stabilized by a large moon. Over long periods of time, Mars's axis can shift dramatically, sometimes becoming much more tilted, sometimes far less. When that tilt changes, where sunlight falls on the planet changes with it. Then there's precession, the slow wobble of Mars's rotational axis, combined with changes in the shape of its orbit, known as orbital eccentricity. This wobble alters how evenly Mars receives energy from the Sun over thousands of years. None of these changes are fast. None of them are dramatic in the moment. But over time, they matter. And they matter more on Mars than they do on Earth. Because Mars's climate is already near the edge of stability, even small shifts can have outsized effects. When the planet tilts more strongly, sunlight reaches regions that are usually cold and dark. Ice that has been locked away at the poles can begin to move, sublimating into vapor, migrating through the atmosphere and settling elsewhere. When that happens, the entire distribution of water changes. Ice doesn't stay where it was. Frost forms in new places. Moisture becomes temporarily more available in regions that are usually bone dry. This doesn't create rainfall or flowing rivers, but it does create conditions where snow, frost, or thin films of briny liquid can briefly exist, especially in low-lying areas and within surface materials rich in salts. Over time, as Mars's tilt shifts again, those conditions fade. Ice returns to the poles. The atmosphere dries out. The surface grows quiet once more. Then, thousands or tens of thousands of years later, the cycle repeats. This is why it's misleading to think of Mars as a planet that simply dried out and stayed that way. Mars may have gone through multiple awakenings, not warm eras like Earth's past, but subtle climate pulses, periods when water became just active enough to interact with the surface, reshape minerals, and leave behind evidence that survives long after the conditions themselves disappear. This framework helps explain what we see in the geological record. Those cemented crusts on dunes, the young sedimentary features that don't fit neatly into an ancient-only timeline. The hydrated minerals found in places that seem far too dry today. They don't require a thick atmosphere or a permanently warm climate. They only require time, repetition, and a planet that keeps tipping in and out of balance. And that's the crucial distinction. These are not seasons. They are eras. Each cycle lasts long enough for chemistry to do real work, long enough for water, however limited, to touch rock, dissolve salts and then retreat, long enough for small changes to accumulate into structures we can still measure. On Earth, such changes might be erased quickly by erosion, vegetation, or tectonics. On Mars, once something forms, it tends to stay. So when scientists talk about late wet episodes, they're not describing a fluke. They're describing a pattern that fits with everything we know about Mars's long-term behavior. A planet that never settled into balance. A world that repeatedly shifted between slightly more active and slightly more frozen states. That instability is often described as a weakness. But in this case, it may have been an opportunity. Because every time Mars tilted just enough, every time ice migrated and moisture briefly returned to the surface, the clock restarted, if only for a while. Environments could form. Chemistry could reorganize. Conditions could align just long enough to matter. Mars didn't have seasons like Earth. It had eras. And those eras may explain how water kept reappearing on a planet that seemed determined to lose it. But even with shifting climates and repeating cycles, Mars was still changing in another, more fundamental way. Because while the planet's surface responded to these long rhythms, something deeper was slowly slipping away. But even with water and climate cycles, Mars was still losing something critical. To understand why Mars changed so profoundly, we have to look beneath its surface, deeper than dust, deeper than rock, deeper even than water. We have to look at what once protected the planet. Every world with a long-lived atmosphere faces the same challenge. The sun. The sun is not just a source of light and warmth. It is also a constant stream of charged particles, solar wind, flowing outward through the solar system. Over time, that wind can strip away a planet's atmosphere molecule by molecule, unless something stands in the way. On Earth, that protection comes from a global magnetic field generated deep within the planet. Earth's magnetic field acts like an invisible shield. It deflects much of the solar wind, guiding charged particles around the atmosphere instead of letting them collide directly with it. Without that shield, Earth would look very different today. Mars once had something similar. Early in its history, Mars was a warmer, more active world. Its interior was hot enough to drive motion within a molten core. That motion, known as convection, generated a global magnetic field, wrapping the planet in a protective bubble. For a time, Mars was shielded, but Mars is smaller than Earth. It cooled faster. As the planet lost internal heat, the motion inside its core slowed. Convection weakened. And eventually, the global magnetic field faded away. The loss wasn't dramatic. There was no explosion, no single moment of collapse. Mars didn't break. It slowly lost its protection. Once the magnetic field weakened, the solar wind gained direct access to the upper atmosphere. Charged particles began to collide with atmospheric gases, transferring energy and knocking atoms into space. At first, the losses were subtle. But over millions of years, subtle adds up. This process didn't remove the atmosphere overnight. It thinned it, gradually, persistently, until pressure dropped too low to reliably support liquid water at the surface. We can see evidence of this process today. In 2014, NASA launched the MAVEN mission, short for Mars Atmosphere and Volatile Evolution. MAVEN was designed to measure how Mars is losing its atmosphere right now. Its findings were clear. Mars is still leaking gas into space. MAVEN observed atmospheric particles being stripped away by the solar wind, especially during periods of increased solar activity. When the sun releases bursts of energy, solar flares or coronal mass ejections, the rate of atmospheric loss spikes. That tells us two important things. First, the process is ongoing. Mars hasn't finished changing. Second, it gives us a window into the past, because the sun we see today is calmer than it once was. Early in the solar system's history, the young sun was far more violent. Solar storms were stronger, more frequent, and more energetic. Without a magnetic field to deflect them, Mars would have been exposed to that intense activity for extended periods of time. The result was a slow but relentless erosion of the atmosphere. As pressure dropped, surface water became unstable. Liquid could no longer persist easily. Water froze, evaporated, or retreated underground. The planet grew colder and drier, not because water vanished all at once, but because the conditions that allowed it to remain were slipping away. This helps explain a puzzle that has long confused scientists. Mars shows clear evidence of water that lasted long enough to shape landscapes, but it also shows signs of environments becoming hostile over time. The planet didn't transition cleanly from wet to dry. It moved through stages. Even as the atmosphere thinned, water didn't immediately disappear. Instead, it became harder to maintain at the surface. Lakes shrank, rivers slowed, ice became more important, and any remaining liquid had to find shelter, briefly appearing during favorable conditions, then retreating again. This is where the story becomes less about catastrophe and more about vulnerability. Mars wasn't destroyed by a single event. It wasn't wiped clean by an impact or boiled dry in a sudden blaze. It faded. As its shield weakened, the planet became increasingly exposed. Each solar storm chipped away a little more. Each passing million years lowered the margin for habitability. That gradual loss matters because it reframes how we think about planetary survival. A world doesn't need to explode to become uninhabitable. It only needs to lose its defenses. When scientists compare Mars and Earth, the contrast is striking. Both planets formed from similar materials. Both once had internal heat. Both likely had water early on. But Earth kept its magnetic field. Mars did not. That single difference shaped everything that followed. On Earth, the atmosphere remained thick. Water stayed liquid. Climate stayed active. Life had time to adapt and spread. On Mars, the clock ran out sooner. As the atmosphere thinned, any life that may have existed on the surface would have faced growing challenges: radiation, cold, dryness. Survival would have required retreat, adaptation, or disappearance. And yet, even this loss was not absolute. Mars didn't erase its past. It buried it. The rocks still carry chemical signatures. The ground still preserves layers shaped by water. The surface still holds clues to environments that once existed under very different conditions. The shield was gone, but the record remained. That's what makes Mars so compelling. It is not a planet that simply failed. It is a planet that came close and then slowly crossed a threshold it could not reverse. Understanding how Mars lost its shield helps us understand why its surface became hostile. But it also helps us see why traces of earlier conditions survived at all. Because even as Mars lost its atmosphere, it never erased everything that came before. And that means the story is not over yet. By the time Mars lost much of its atmosphere and magnetic protection, the surface of the planet had begun to change in a very specific way. Not dramatically, not all at once, but steadily, until the surface became one of the most hostile environments in the solar system. Today, Mars sits exposed beneath a thin sky. Its atmosphere is so sparse that it offers little protection from radiation arriving from space. Ultraviolet light from the sun reaches the ground almost unfiltered. High-energy cosmic rays, born in distant stellar explosions, pass through the atmosphere with ease and strike the surface directly. On Earth, we rarely think about this kind of radiation. Our thick atmosphere and magnetic field absorb or deflect most of it before it ever reaches the ground. On Mars, that shield is gone. The result is a surface constantly bathed in radiation, day after day, year after year. This matters because radiation doesn't just damage living cells, it also alters chemistry. It breaks molecular bonds. It reshapes the environment in ways that make long-term biological activity extremely difficult. And that's only part of the problem. Mars's atmosphere today is less than 1% as dense as Earth's. With such low pressure, liquid water is unstable at the surface. Even when temperatures briefly rise above freezing, water tends to evaporate or boil away rather than pool or flow. Any moisture that appears must do so fleetingly under very narrow conditions. Then there is the soil itself. Across much of Mars, scientists have detected perchlorates, salts that form naturally under Martian conditions. On their own, perchlorates are already challenging for biology. But when exposed to ultraviolet radiation, they become even more reactive, producing compounds that are highly destructive to organic molecules. In other words, the very ground on Mars can work against life. Add to that the planet's fine dust. Martian dust is extremely small, easily lifted, and electrostatically clingy. It coats surfaces, blocks sunlight, and can interfere with delicate chemical processes. For any hypothetical organism trying to survive at the surface, this combination, radiation, reactive soil, low pressure, and abrasive dust, would be overwhelming. Taken together, these factors close the door on a simple idea. The surface of Mars is not where life would survive. Not today, and not for a very long time. That conclusion doesn't come from a single observation. It comes from many lines of evidence converging on the same answer. Mars's surface has become a place where exposure is constant and protection is minimal. If life ever existed there, remaining on the surface would have been a losing strategy. But this is where the story takes an important turn. Because Mars is not a static, lifeless rock. In 2018, NASA's InSight lander touched down on the planet to study its interior. Instead of looking outward, InSight listened. And what it detected were Marsquakes, vibrations traveling through the ground. Mars, it turned out, is still active beneath its surface. These quakes revealed information about the planet's internal layers, its crust, mantle, and core. They showed that Mars is not completely frozen inside. Heat still moves, energy still shifts. The planet continues to change, even if that change is slow and subtle. That matters, because if the surface is too harsh, and the interior still retains warmth, then the most reasonable place to look for survivability is not where Mars is exposed, but where it is sheltered. Radiation weakens with depth. Temperatures become more stable. Chemical reactions slow and settle. On Earth, we found life thriving deep underground, far from sunlight, living off chemical energy alone. These organisms don't need open air or warm oceans. They need protection, water, and time. Mars may have offered something similar. The hostile surface doesn't erase the possibility of life. It simply forces the question to move. Not whether Mars could support life at some point, but where that life could persist as conditions worsened. The planet's history suggests a retreat. As the surface grew more dangerous, any surviving chemistry or biology would have been pushed downward, away from radiation and instability, toward environments that changed more slowly. Mars may look dead from above, but the processes beneath its surface tell a different story, one of endurance rather than collapse. The surface of Mars is not where life would survive. So the real question becomes, where could life have gone? By now, one question naturally rises above all the others. If Mars once had so much water, enough to carve valleys, fill lakes, and shape entire regions, then where did it all go? Because when we look at Mars today, the surface appears almost completely dry. No rivers, no oceans, no standing bodies of liquid water that last more than moments. For a long time, the simplest answers sounded like this: Mars lost its water. But that turns out to be misleading. Mars didn't lose its water. It redistributed it. Some of that water is still visible, locked away at the planet's poles. Vast ice caps, made mostly of water ice, layered with seasonal carbon dioxide frost, store enormous amounts of frozen water. These polar reservoirs expand and contract with the seasons, but they have persisted for millions of years. Yet the poles are only part of the story. Beneath much of Mars's surface lies permafrost, ground that remains frozen year-round. In many regions, just a short distance below the surface, ice-rich layers have been detected by radar and confirmed by exposed scarps, where erosion has revealed clean, bright ice. In some places, this ice is so pure it looks freshly cut, as if it were placed there yesterday rather than buried for geological ages. This means Mars is not dry in the way a desert on Earth is dry. It is dry at the surface, but wet just beneath it. Then there is a third, less obvious reservoir. Water on Mars is also stored inside rock itself. Across the planet, scientists have identified minerals that form only when water is present: clays, sulfates, and other hydrated minerals. In these materials, water isn't sloshing or frozen. It's chemically bound, Individual water molecules are locked into crystal structures through chemical reactions that occurred long ago. Once trapped this way, water becomes incredibly stable. It doesn't evaporate, it doesn't freeze or melt. It simply stays, hidden, but not gone. Taken together, these reservoirs change the picture completely. Mars didn't experience a clean break where water vanished from the planet. Instead, as the atmosphere thinned and surface conditions worsened, water migrated to safer forms and safer places. It froze. It seeped downward. It bonded with minerals. The planet adapted. And that adaptation matters for one reason above all others. Because water doesn't need to be visible to matter. If water exists below the surface, protected from radiation, shielded from extreme temperature swings, and occasionally warmed by internal heat, then it can still participate in chemistry. It can still move, slowly. It can still interact with rock. And in the right conditions, it can still support environments that are far more stable than the surface ever became. This reframes the central question. The question is no longer, did Mars lose its water? The better question is, where is the water now, and what form does it take? Because once water retreats underground, the rules change. Below the surface, pressure increases. Radiation fades. Temperatures become more predictable. On Earth, some of the most resilient life we know exists deep underground, far from sunlight. These organisms don't depend on surface conditions at all. They live slowly, feeding on chemical energy released by interactions between water and rock. Mars may have offered similar niches. Not vast underground oceans, not bustling ecosystems, but pockets, zones, places where water, chemistry, and time overlapped long enough to matter. This is why the disappearance of surface water doesn't end the story of habitability. It redirects it. Mars didn't become lifeless overnight. It became hidden. And once you accept that water is still present, frozen, buried, or bound into stone, the idea that life simply vanished becomes less certain. If life ever took hold, it may have followed the water downward, adapting as the planet changed around it. Mars didn't lose its water. It hid it. And that realization prepares us for the next step in the story. Because as you move deeper beneath the Martian surface, something else begins to change as well. Temperatures rise, conditions soften, and the deeper you go on Mars, the warmer things become. Once you accept that Mars still holds water, frozen, buried, or locked inside rock, the next question becomes unavoidable. If the surface is too harsh, and the water has retreated downward, then what does the world beneath the surface look like? Because planets don't end at their skin. As you move deeper underground, conditions change in predictable ways. Temperature rises with depth. Pressure increases. Materials behave differently. What feels frozen and lifeless at the surface can become more stable just a few kilometers below. Mars is no exception. Even today, heat still flows outward from the planet's interior. It's weak compared to Earth, but it's not gone. That slow, persistent heat creates a gradient. Cool at the surface, warmer below. In the right places, at sufficient depth, temperatures could cross a critical threshold. Cold ice becomes something else. Liquid water. Not lakes or rivers, but water trapped inside fractures, pores, and cracks in rock, forming deep aquifers that move slowly and quietly through the crust. This idea isn't speculative. It's grounded in physics. Water under pressure can remain liquid at temperatures where it would otherwise freeze. Salts can lower freezing points further, and rock is an excellent insulator. Once water retreats underground, it can remain stable for extremely long periods of time. On Earth, We know this kind of environment very well. Some of the most resilient life forms ever discovered live deep within our planet's crust, kilometers below the surface, far from sunlight. These organisms survive on chemical energy alone. They feed on reactions between water and rock. They grow slowly. They endure. They don't care about seasons. They don't care about climate at the surface. They care about stability. And that's exactly what the Martian subsurface could provide. Down there, radiation drops off sharply. Cosmic rays weaken with every meter of rock above. Temperature swings disappear. The chaos of the surface gives way to a quieter, slower world. One where change happens over thousands or millions of years, not hours. This is why scientists increasingly see deep aquifers as the most plausible long-term refuge for life on Mars. Not everywhere, not all the time, but in specific zones, where fractures allow water to move, where heat lingers, where chemistry can keep going. Of course, this idea has limits. Liquid water alone is not enough. Any living system needs energy and nutrients. In Earth's deep biosphere, microbes often rely on chemical gradients created by interactions between water and minerals, processes like serpentinization, where rock reactions release hydrogen and other usable energy sources. Mars has the right kinds of rocks. Mars has a history of water-rock interaction, and Mars has had vast amounts of time. What it lacks is certainty. We don't yet know how widespread these deep aquifers might be. We don't know how connected they are, and we don't know whether conditions remain stable long enough for life to persist, adapt, or even begin. But the idea itself is not science fiction. It is conservative. It follows known physics, and it mirrors what we already see on Earth. If life ever emerged on Mars, when the surface was warmer and wetter, it wouldn't have needed to vanish when conditions worsened. It could have retreated, slowly, incrementally, following the water downward as the planet changed above it. Mars doesn't need to be alive everywhere to matter. It only needs to have been alive somewhere. And that possibility reframes the entire search. Instead of scanning wide landscapes for obvious signs, scientists must think vertically, through layers of rock, through time, through environments that are invisible from orbit. Mars may look quiet today, but beneath its silent surface, the planet may still hold places where chemistry never stopped. Places where water, heat, and rock continued their slow conversation long after the surface became hostile. This is the hidden world of Mars. Not a fantasy, not a lost ocean, but a set of environments shaped by retreat and survival. A final refuge, not a final failure. And just as this idea began to take shape, after decades of searching, drilling, and debate, something unexpected appeared at the surface. Not a river, not an ocean, but a rock. A single rock that would change the conversation. And then, after years of silence, one rock changed the conversation. This moment begins quietly. No announcement, no alarm. Just a rover moving slowly across the floor of an ancient crater. By the time Perseverance arrived at Jezero Crater, scientists already knew this place mattered. Billions of years ago, Jezero held a lake. Rivers once flowed into it, carrying sediment from the surrounding highlands. Where those rivers slowed, they dropped layer after layer of fine material, mud, silt, minerals, building a delta that hardened into rock. On Earth, environments like this are remarkable record keepers. They trap chemistry, they preserve texture, they store history. That's why Perseverance was sent here. And one day, while examining sedimentary rock formed in that long-gone lake system, the rover found something unusual. At first glance, the rock didn't look dramatic. It wasn't towering or jagged. It didn't glow or shimmer. It was flat, layered, and ordinary. Exactly the kind of rock you might overlook. Until you looked closer. Scattered across its surface were tiny dark spots, each about the size of a poppy seed. Small, subtle, easy to miss if you weren't looking carefully. But these spots weren't random. They appeared in clusters. They repeated. They followed patterns. Scientists began calling them leopard spots, not because of their color alone, but because of how they grouped. Small, dark centers surrounded by lighter halos, repeating across the rock in a way that felt organized rather than accidental. The scale matters here. These features are measured in millimeters. If they have anything to do with biology, we are not talking about plants or animals. We are talking about microbes. Organisms so small that their presence would only ever be inferred through what they left behind. And that distinction is critical. Perseverance did not find life. It did not see cells. It did not detect organisms moving or growing. What it found were patterns. And in science, patterns are often where the most important questions begin. The rover's instruments revealed that these dark spots are associated with specific chemical changes in the rock, variations that suggest past interactions between minerals and fluids. On Earth, similar features can form when microbes influence chemical reactions in sediment, leaving behind localized mineral deposits. But, and this matters deeply, non-biological processes can sometimes produce similar effects. That's why scientists didn't celebrate. They slowed down. Because the history of Mars has taught them caution. Sedimentary rocks are valuable precisely because they form slowly, in layers, under stable conditions. Each layer captures a moment in time. Each chemical gradient preserves an environmental snapshot. If water chemistry changed, if minerals dissolved and reformed, if something interacted with the rock repeatedly, those changes can become locked in place. This is what makes sedimentary environments such powerful archives. And it's why this rock drew so much attention. The leopard spots weren't sitting in isolation. They were embedded within a rock that already told a story of water, of a lake that lasted long enough to build a delta, long enough for fine sediments to settle gently out of suspension. That context matters. A random rock with strange markings is curiosity. A sedimentary rock formed in water with repeated, organized chemical patterns is something else entirely. Still, scientists were careful. They did not say these spots were fossils. They did not claim they were biosignatures. They did not announce the discovery of a life. Instead, they asked a narrower, more disciplined question. What processes could produce this pattern? Some possibilities are entirely geological. Chemical reactions driven by changes in water chemistry, temperature, or mineral composition. Mars has a long history of complex chemistry, and not all patterns require biology. But some features are harder to explain without invoking repeated, localized interactions between fluids and rock, interactions that, on Earth, are often associated with microbial activity. That tension is the heart of the discovery. This isn't a fossil, it's a pattern. And patterns don't declare their origin. They invite investigation. The significance of the leopard spots is not that they prove life existed on Mars. It's that they narrow the gap between maybe and plausible. For decades, Mars exploration has moved in stages. First, was there water? Then, was it stable? Then, could it support life? This rock touches all three. It sits in an environment that was once wet. It formed under conditions that allowed chemistry to repeat and organize. And it carries features that resemble the kind of chemical fingerprints life can leave behind, without crossing the line into certainty. That is why this moment feels different. Not louder, not more dramatic, just sharper. For the first time, the conversation isn't centered on ancient rivers seen from orbit or abstract models of habitability. It's centered on a specific object, in a specific place, carrying specific features that can be studied, debated, and eventually tested. And that final step matters, because perseverance is not just a rover, it is a collector. Some of the most intriguing samples it finds, including rocks like this one, are being sealed and cached, waiting for a future mission to bring them back to Earth. Only then can they be examined with the full power of laboratory instruments, tools far more sensitive than anything that can be sent to Mars today. Until that happens, the leopard spots remain a question mark. A disciplined one, a careful one. They don't shout, they whisper. And they remind us of something important. Science doesn't move forward by declaring answers. It moves forward by identifying the most interesting uncertainties. This rock doesn't tell us that Mars was alive, but it tells us that Mars may have come closer than we ever realized. And that possibility, quiet, unresolved, and grounded in real data, is why this discovery matters. Because in planetary science, the most important moments are rarely the ones that end a debate. They're the ones that force us to take a much closer look. But patterns alone are never enough. At this point in the story, it's tempting to rush toward a conclusion. There is water in Mars's past. There are stable environments. There are rocks with repeating patterns. But this is where science slows down on purpose, because the most important questions are often decided not by excitement, but by restraint. When researchers examined the leopard-spotted rock more closely, they noticed something else worth careful attention: the minerals involved. Some of the dark spots are associated with iron-rich compounds, minerals that, on Earth, often appear in environments shaped by microbial activity. That connection is real, but it is also incomplete. On Earth, microbes frequently influence iron chemistry. They can change how iron oxidizes and precipitates, leaving behind localized mineral patterns. Over time, those patterns can become locked into sedimentary rock. But iron chemistry does not belong exclusively to biology. Under the right conditions, changes in temperature, acidity, or fluid chemistry, purely geological processes can produce iron-rich features that look surprisingly organized. Mars, with its complex history of water, salts, and shifting conditions, offers many opportunities for such reactions to occur. So, iron alone is not enough. Then there are organic molecules. Over the past decade, multiple Mars missions have detected carbon-based compounds in Martian rocks and soil. These are not contaminants brought from Earth. They are indigenous to Mars, formed by chemical processes that don't require life. And this distinction matters. Organic molecules are not evidence of biology. They are ingredients. They are the basic building blocks of chemistry. Carbon chains that can form in many environments, from interstellar clouds to volcanic systems. On their own, they tell us nothing about whether life ever existed. But context changes meaning. When organic compounds appear alongside certain minerals, within rocks that formed in water, inside environments that were once stable and long-lived, the picture becomes more interesting, not conclusive, but harder to dismiss. This is the line scientists must walk. On one side is caution, informed by history. In 1996, a Martian meteorite found in Antarctica was announced as possible evidence of ancient life. The claim was dramatic. The reaction was immediate. And over time, alternative explanations emerged that weakened the biological interpretation. Earlier still, the Viking landers detected chemical reactions in Martian soil that initially looked like signs of life, only to be explained later by non-biological chemistry unique to Mars. Those lessons remain fresh. They taught planetary scientists that Mars is exceptionally good at producing false positives. It can mimic the signals of life without ever hosting it. That's why standards have changed. Today, no single observation is allowed to carry the weight of a claim. No pattern, mineral, or molecule is enough by itself. Evidence must converge. Independent lines must agree. Context must be airtight. This is why scientists repeat a phrase that sounds almost stubborn. Extraordinary claims require extraordinary evidence. It's not a slogan, it's a safeguard. The leopard spots sit right on that boundary. They involve minerals that, on Earth, are often associated with biology. They occur in sedimentary rock formed in water. They appear alongside organic material. And yet, none of this forces a biological explanation. At the same time, none of it rules one out. That tension is what makes the discovery important. Science does not say, "This is life," but it also does not say, "This cannot be life." Instead, it says something more precise. This is the kind of environment where life could have left a trace. That may sound subtle. It may even sound unsatisfying. But in planetary science, that is how progress looks. Certainty arrives slowly. It arrives only after alternatives are exhausted, samples are tested, and questions are allowed to remain open longer than we'd like. That's why perseverance didn't stop with observation. The rover is collecting samples, carefully chosen pieces of Mars's geological record, and sealing them away. These samples are designed to wait years, perhaps decades, until future missions can return them to Earth. Only then can scientists apply the full range of laboratory tools, microscopes, mass spectrometers, chemical analyses far beyond what a rover can carry. Only then can the question move closer to resolution. Until that moment, the line remains where it should be. Careful, disciplined, honest. Mars has given us minerals. It has given us organics. It has given us environments that make sense. What it has not yet given us is proof, and that restraint, uncomfortable as it is a strength, not a weakness. Because it means the story is not finished. It means Mars is still asking us something. And that brings us to the biggest question Mars has ever asked us. By now, the shape of Mars's story has become clear. This was not a planet that was always cold and empty. Mars once had water, moving across its surface, collecting in lakes, interacting with rock over long periods of time. It had the conditions needed to shape landscapes and chemistry in ways that feel familiar. But Mars also changed. Its interior cooled, its magnetic shield faded, its atmosphere thinned. As protection weakened, the surface grew harsher. Liquid water became unstable. Radiation increased. The planet slowly crossed a line, from a world that could support surface environments to one that could not. And yet, the story did not end there. The water did not vanish. It froze at the poles. It retreated beneath the surface. It locked itself into minerals. Mars adapted, even as it declined. We've seen evidence of late wet episodes, subtle, intermittent returns of moisture long after the planet was assumed to be dry. We've seen signs that chemistry continued, quietly, beneath the surface. And we've seen something even more intriguing. specific rocks formed in water-rich environments, carrying patterns that force scientists to pause and look closer. Not answers, but questions sharpened by context. At the same time, it's important to understand what science has not done. No rover has confirmed life on Mars. No instrument on the surface can make that claim. The tools we send to another planet are remarkable, but they are limited. They must be light, durable, and able to survive years of isolation. They can analyze chemistry, texture, and structure, but they cannot replicate the depth of a full laboratory on Earth. That's why the most important discoveries on Mars are still incomplete by design. Perseverance is not trying to finish the story. It's trying to preserve it. By collecting carefully selected samples, sealing pieces of Mars's geological record inside metal tubes, the rover is preparing for a future moment when those rocks can be brought home. Only then can scientists examine them with the precision required to distinguish biology from chemistry, life from coincidence. That future mission, Mars Sample Return, is complex, expensive, and uncertain. It involves multiple launches, robotic handoffs, and years of planning. There is no fixed date. There is no guarantee. But the intention matters, because it shows that science is willing to wait, and waiting changes the way we think about the question itself. If Mars once had life, then life may not be a rare accident confined to Earth. It may emerge wherever conditions allow it enough time and stability. And if Mars never had life, despite water, chemistry, and opportunity, then the existence of life on Earth becomes even more remarkable. Not less meaningful, but more. Either outcome teaches us something important. This is where Mars becomes more than a destination. It becomes a mirror. Mars shows us what happens when a planet loses its protection, when its atmosphere thins, when its internal engine cools, when the balance that allows water and potentially life to persist quietly slips away. There was no single disaster, no dramatic collapse. Mars didn't explode, it faded. That lesson matters because Earth is not guaranteed permanence. Our planet remains alive because it still holds its atmosphere, its magnetic field, and its internal heat. These systems work together, silently, every day, creating stability we rarely notice. Mars reminds us that such stability is fragile. It doesn't shout this warning. It doesn't dramatize it. It writes it slowly, in stone, in layers, in the quiet absence of what once was. And perhaps that's why Mars is so compelling. Not because it promises answers about life elsewhere, but because it helps us understand the conditions that allow a living world to endure. As the story ends, the largest question remains open, not as a problem to be solved tonight, but as something to sit with. The question is no longer simply, are we alone? It is, how fragile is a living world? Mars doesn't demand an answer. It offers perspective. And in that perspective, there is something calming. Worlds change slowly. Science moves carefully. Understanding arrives in layers. Tonight, Mars reminds us that worlds can change quietly, and that the one we live on is worth protecting.